All right, some questions to think about. Just to review what was discussed before break. Got a picture here. You got a portal system. Okay. And which cat bed is this? One, two. It's all blue. Portal veins connect, which is what B is pointing to. So that answer is A. And the hormones that it transports, we probably don't have them all memorized now, but it's the ones that will be secreted from here, all those tropic hormones. And as we were taking notes, they were in this column, right? Yeah, and on the exam, that B question, I have the toughest time getting guys to remember. There's a lot of hormones, and you get the ones secreted from here mixed up with these down here. That seems to be the biggest mistake on the first exam. So try to keep that straight in your head. And here, C, one word answer. What type of connection is this? Did I call it vascular or neural? Vascular, right? Because it's a blood vessel that connects the two. All right, here is the control of the posterior pituitary. If you identify A, B, and C, A, that's the stalk. B has a lasso around those tractive axons. We called it the hypothalamic hypophyseal tract. That's what I said, put a star next to that. Try to remember that term. It's a difficult term to remember. Well, C is just pointing to the posterior lobe. Okay. There's the optic chiasm. It's a different book. And it's a mirror image. We kind of flipped it. And so you have to be able to transplant your knowledge from figure to figure. That would be helpful. That's kind of why I took that from a different book to show students. We're not going to keep things the same for you. We teach concepts, and you apply the concepts to whatever is shown to you on exams or quizzes. I want to flip the page on pituitary and start the next gland on Endocrine Lecture 3. And we're going to start with the adrenal gland, or suprarenal gland as it's also known as, on top of the kidney. The adrenal gland, also called suprarenal gland, renal refers to kidney, as you can see here, is basically a stress response gland. Cut it open. I mentioned this the last time. You have a cortex medulla surrounded by a capsule. Capsule surrounds the adrenal cortex and medulla. Remember, cortex in anatomy is a word that means bark. It's the outer part. Medulla means pith, like a pit. It's in the center. Maybe that'll help you remember cortex and medulla. Now they have different functions, okay? As I say on the slide, the outer region, the cortex, they secrete corticosteroids that'll help you deal with long-term stress response. So that's what I'm writing. The adrenal cortex secretes corticosteroids. They help you deal with stress over the long term. So days, weeks, months, maybe even years, depending on the situation. So we say long-term stress responses. Survival situations. My wife and I used to watch that Bear Grylls. He used to drop them off in some remote land and he tells you how to survive. That kind of stress. If you're a prisoner of war, that kind of stress. You're stranded on a boat, lifeboat somewhere for days or weeks. And how does the body keep itself alive? These are the kind of hormones we'll talk about. Okay, in the adrenal medulla, those are the catecholamines. They secrete catecholamines. I mentioned those yesterday. Those will help you deal with short-term stress. So, minutes, seconds, maybe hours, depending on whatever you're dealing with. My son last week, he jumped off the railing of our stairs. Totally freaked me out. I was having a short-term stress. I was freaking out. Well, that kind of thing. I take your son to ER and that kind of thing. It's stress, right? He's okay. He's fine. No broken bones. He's like Superman. I don't know how he does that. 20-foot jump. Didn't break any bones. But anyways, that is an example of things that stress us out in the short term. Minutes, hours, maybe. And yeah, epi, norepi are your catecholamines. Epinephrine, norepinephrine are the full names. Epi, norepi. Okay, moving on. Well, let's kind of dissect this a little further. Okay, this is kind of a gritty picture, which lets you know it's part of our collection, right? It's not a pristine picture from the internet. This is what you have to deal with when we do our lab and when we do our quiz. I'm going to test you on the stuff we have. Okay, there's pros and cons. Oh, good. We'll get the images, but they're not ideal. Okay. It's very important that you distinguish, that you identify the capsule. Otherwise, you'll confuse it with part of the cortex, because there are different zones in the cortex you have to identify. Try to train your eye to see the border between cortex and medulla. That's a big one. Once you can see this border, then, oh, okay, you can identify the three zones you got to know, and then this is all just medulla catecholamines. So I'll take you through that. Here's kind of like a professional picture from the web. We have these different zones, which I'll define. Okay. One is pointing to this whole area, adrenal medulla. This outermost zone, the darkest one in this slide, is zona glomerulosa. This lighter stained zone is zona fasciculata. And the innermost zone of the cortex, where the 2 is zona reticularis, zona for zone. Because they secrete different hormones. And the figure from your book that we'll use to teach this is shown here. And I like how they have the illustration next to histo. And I also like how the illustrators put red blood all sandwiched in between here, because remember, corticosteroids need access to the bloodstream, as do all hormones. Again, it helps to identify capsule, a fibrous, dense, regularly connected tissue. Then you have all these other zones of the cortex. So let's kind of talk about those. Three zones of the adrenal cortex. Now the outermost zone is called zona glomerulosa. And let's kind of examine what we're looking at here. They're showing you capsule, cortex, and medulla. A little patch right here. So you're looking at a little section of a gland, and when I look at a microscope slide, it's kind of the same deal. You just kind of see a patch. You don't see the whole gland in view. You just see kind of part of it here. In this outermost zone, the cells are arranged in little oval clumps. They look like little balls of yarn. So I'm just writing cells are oval in their arrangement. Now when we look at microscope slides, you're not always going to see that. The main thing that will help you is if just remember it's the outermost zone. Not the outermost thing, the outermost zone. Remember, the outermost thing is the capsule. That's why you got to be able to identify the capsule. In fact, this word root, glomer, means ball of yarn. So the name of the zone is how the cells are arranged, basically, for these zones. Now, what you got to know is the secretion. These secrete a class of corticosteroids called mineral corticoids to help regulate electrolytes. You only got to know one of this class of hormones. No aldosterone. That's the one. It helps sodium reabsorption. It helps keep blood pressure up. That'll help you in a long-term stress response. All right, the next zone where the cells are arranged in these vertical cords is zona fasciculata. And that's what fasciculata means. It means cords. So it's kind of the middle zone. And they secrete a class of hormones called glucocorticoids. And there's only one you got to know, cortisol. Now the innermost zone is usually thinner on slides that I look at, but anyways, they illustrate it like this here. It's the one that borders next to medulla. It's the zona reticularis. Reticularis means like, complex network. So there's no organized arrangement of the cells in this layer. Okay, so zona reticularis. They secrete sex hormones. I'll say it's the inner zone secretes sex hormones. I won't say too much about them. The majority of the sex hormones are from the gonads, not the adrenal cortex. But maybe it's really not known the true function of the sex hormones from the adrenal gland. Maybe they help kick off puberty or something like that. We don't really need to be concerned with it. Just know they secrete the sex hormones. Those are the three zones. And here's a labeled picture from our collection that I took a picture of years ago. You kind of see, I'll turn the lights off, maybe we can see the image slightly better. Capsule. Zona, glomerulosa, fasciculata, reticularis is shown there. Okay. I can even kind of see little ovals right there. And these kind of look more like straight. Okay. And so if you can see the border between cortex and medulla, like on your quiz for Friday, if I point like way down here, I'm going for medulla. But if I point to like what looks to be close to the border, I'm going for zona reticularis. If I point to the middle of the cortex, fasciculata. The outermost zone is glomerulosa. Okay, remember, not the capsule. The capsule is not a zone. It's just a capsule. So I have salt, sugar, sex as a little memory jogger. What is salt referred to? Mineral corticoids. What does aldosterone do? Reabsorbs sodium. That was on today's quiz. Did you get it? Salt. Sugar refers to sodium fasciculata, cortisol. It helps increase circulating levels of glucose. I'll show you how. And the sex hormones. Okay, salt, sugar, sex corresponding to the three zones: glomerulosa, fasciculata, reticularis. Salt, sugar, sex. Adrenal cortex secretes corticosteroids, the salt, the sugar, and the sex. The epi and norepi know that too, secreted in about a ratio of 80-20. Okay, that's for the short-term stress response. So we talked about that. And I have this slide, and you don't have to memorize this cascade. There are cascades you do have to memorize for this test, but not this one. One thing I would note, I put arrows next to all the hormones you gotta know. Also, they're all derived from cholesterol. Okay? These are all the steroid hormones. One thing I want you to know, the difference between males and females hormonally is due to the enzyme aromatase. It's converting androgens into estrogens. Let's note that. That'll come up again in repro. Got androstenedione. You got testosterone. They're both converted to estrogens. Estrone, estradiol, which is the chief estrogen. Estrogen is a class of hormones. These are two chief ones, according to, well, a lot of books. But anyways, the conversion of androgen to estrogen is through aromatase. The researchers who study sex differentiation, they study aromatase. It's important in development. I want to talk about the physiology of some of the corticosteroids a little more. Starting with zona glomerulosa, the one you got to know, aldosterone. We learned on Monday it helps maintain the blood pressure, right? You increase the blood volume, that helps raise or maintain the blood pressure. Okay? Pressure is the driving force that pushes blood from your heart all the way out to the capillaries. If you don't have that pressure, blood fails to circulate, and obviously that leads to shock and death. So anyways, getting back to aldosterone, there are ways to stimulate its release, and there's one way you can inhibit it. So the thing you're trying to regulate is blood pressure. And here's a figure from the book that kind of helps you understand that. I have it outlined what you need to know. Well, let's kind of look at the picture too. So it's three mechanisms to stimulate its release. Here's zona glomerulosa, and one way to inhibit it. If blood pressure is too high and you want to lower it, I'll start with this one. Atrial natriuretic peptide released from the heart can help inhibit its release. So here's the thing here. Blood pressure too high. It's all about what you're trying to regulate. BP. BP is too high. You want to lower it. AMP can help. One way it does it is you inhibit aldosterone. That should help lower it. Okay? Now, if you want to do the inverse, BP is too low, maybe in the face of low sodium or dehydration, bunch of ways. There's a renin the kidney can release a renin. There's a cascade effect I want you to know. That can lead to aldosterone. I'm going to call it RAAS. Okay, I'll define that later. Another way is a humoral effect. If there's low sodium in the blood, that's a direct stimulating effect on the zona glomerulosa. Low sodium can directly affect the zona glomerulosa. Thirdly, the stress of being dehydrated. Usually if you're dehydrated, you're stressed probably. CRH, ACTH, right? That whole thing. That can have an effect to its release. ACTH. Okay, all three of these things stimulate the release of aldosterone. To increase BP. Okay, the one I'm going to really have you know for the exam is this one. I want you to know the whole cascade, and I want to outline it for you. But I want to mention the other things. Low sodium, ACTH, they can also stimulate its release. We're trying to regulate blood pressure here in a long-term stress response. That's the physiology that's going on. All right, RAAS. I like to really unpack this one because it comes up again in cardio and in kidney. So it's good to really know all the details now. The first R stands for renin. The kidney helps regulate fluid balance. So if you're dehydrated, you probably also have low sodium, because when you sweat, you lose the electrolytes too. The kidney will release renin. What you should also know is that renin is entering the bloodstream here. I'll draw a little blood vessel. But the liver is always secreting this other molecule that's usually inactive. It's called Angiotensinogen. Here, it's a long word. Angiotensinogen. Big long word. Anyways, they're both in the bloodstream. Renin is a cleaver. It'll cleave off the end of this molecule to make it active, because angiotensinogen, big long word, was inactive. So renin cleaves angiotensinogen into what we call angiotensin 1. Angiotensin 1 is also inactive. When it flows to the pulmonary capillaries, there's another enzyme that's a cleaver called ACE. Angiotensin 1 goes to, that's in your lungs, pulmonary capillaries. There's a hormone called ACE, and what will happen is, I'm going to abbreviate angiotensin 1, ANG1. ACE will convert angiotensin 1 into angiotensin 2 by cleaving it, cleaving the end off. ACE also is a cleaver. Cleaves. So we recap. It's a long cascade. The trigger is we're trying to keep you alive. We're dehydrated. We're stressed out. The first hormone is renin. Renin is a cleaver. It's going to cleave Angiotensinogen into Angiotensin 1, or Ang1 for short. That gets to the pulmonary capillaries where Ang1 is converted to Ang2 by ACE. Angiotensin 2 is kind of like the active molecule in this cascade. It'll do a couple of things. One, it will target zona glomerulosa. To secrete the second A of RAAS, that's aldosterone. However, before I leave angiotensin 2, it has a direct effect to increase blood pressure by vasoconstricting arteries. So there's another line from it. Vasoconstrict arteries. That has the effect. When you constrict arteries, you restrict blood flow. You increase the peripheral resistance. That helps to keep blood in the arteries to help keep blood pressure up. Well, anyways, aldosterone, as we talked about it before, it goes back to the kidney to facilitate water reabsorption. As we said last time, that'll increase blood volume, increase blood pressure. As well as the vasoconstriction of arteries. Okay, that's where it ends, finally. You increase the blood volume and vasoconstrict, both help elevate the blood pressure. And let's remember, so this is where we're ending. This is where we began. Because when you're dehydrated, there's low sodium. What you could assume is, just to keep it simple, there's low BP. So ultimately that was what we were trying to correct. And the RAS mechanism has a direct effect at increasing the blood pressure. And this is how, two ways. Through Angiotensinogen, the vasoconstriction and the increasing of the blood volume. And in fact, these two things is very important. This is the only way your body can help elevate blood pressure to keep you alive in any situation. Now, when I do these things, I just kind of go wherever there's a white space on the board. I put a professional picture in it. If you had trouble following me on that, it's here, and you can just follow the steps. Yeah.
So we talked about like
Aldosterone?
Goes back to the kidney
Yeah.
and it helps the kidney reabsorb the water
Yeah.
and the sodium as well, and the electrolytes as well.
Yeah, I should throw that in there. Because what I said is you have the reabsorption of sodium, but what I said water follows, right? So I should probably include the sodium. That's the main job. Thank you. And that should be here too. Let's follow the steps. Start with dehydration, decrease in blood volume, decrease in blood pressure. That's all they stated, right? The kidney secretes renin. The liver also secretes Angiotensinogen. So renin is a cleaver. It cleaves Angiotensinogen into Angiotensin 1. They have a picture of the lungs. You go to the lung capillaries, where ACE, which stands for Angiotensin converting enzyme. angiotensin converting enzyme. It converts Ang1 and Ang2. And Ang2 does the physiology. One, vasoconstriction of the arterioles. Those are the smallest arteries. Well, anyways, that increases blood pressure. The second thing, you go to zona glomerulosa, you increase the aldosterone, and in the kidneys, you increase, like we said, sodium and water reabsorption. Therefore, you increase blood volume, and then you increase blood pressure. Okay, so if you're ever wondering what physiology is, this is it. Memorizing cascades. Using this molecule, it all makes sense to you. You got different organs here, and they're all working together. And that's physiology. And so, doctors have figured this out. If you know a cascade, and you can come up with a drug that affects the cascade, you can help a patient. A lot of people suffer from hypertension, blood pressure too high. So, if blood pressure is too high, if that's the problem, what do you want to do? Lower it. ACE inhibitors can help. Now, you don't have to memorize this picture, but in our picture, where was ACE? The angiotensin converting enzyme. Here it is. If you inhibit ACE, what's the levels of Ang2, up or down? Down. Therefore, what's the level of aldosterone, up or down? Down. That should help decrease blood pressure. So that's the thinking behind ACE inhibitors, and that answers those questions here. ACE inhibiting drug. So that's zona glomerulosa, that's aldosterone. Fasciculata, I wanted you to know cortisol. Cortisol. So what I just erased, I would memorize that for the exam, being able to write that out. It's like one of my favorite things is what I just erased. Instructors emphasize different things. I emphasize that one. One thing you should know about me and about how I give my tests, there's a multiple choice part and a written part. And when I give exams, I post it in the gradebook as 2 scores. And that really helps me assess students later. Say, a couple years later, you come back and ask me for a letter. And one of the things I do, I go back and I review your grades. And I'm able to see multiple choice versus written. It's like, if you're doing really poorly on one area, it kind of helps me, right? So, it's important, it's important for you to know that I see both years down the line. Cortisol. Now, cortisol, if I could take all the information I wrote here and boil it down to one thing you need to know, basically, the prime effect is gluconeogenesis. That's the main effect of cortisol. Okay. Gluco underlying neogenesis. Neo means new. What you're doing is you're creating new carb. Basically, you're making carb. Sometimes I abbreviate carb CHO because the molecular formula is C6H12O6. That's my shorthand for carb. So you make carb from non-carbohydrate sources. namely fat and protein. That's why it's new. I mean, the main way you get glucose in the blood is just to break down your own glycogen stores, but that's your carb. But now you're going to make carb from things that aren't carb. You're just breaking apart the atoms and making new molecules. Cells can do this. That's what's amazing about cells. Okay, so how is this helping us in a stress response? Think about it. You're not able to eat for days. The only thing your brain can metabolize for fuel is glucose, because larger molecules can't get past the blood-brain barrier. So the body is well trained to save glucose for the brain. That's really the goal here. That's a book, right? I see that in books all the time. Save glucose for the brain. You have glycogen stores, right? But you want to save it. It's literally like your savings account in the bank. You got, I don't know, a few grand in savings, let's say. Okay, you're doing well. When you get tight at the end of the month, sometimes you have to tap your savings. And don't you hate doing that? I do. I don't want to use my savings. It's savings. So it's there. You know, the body's the same way. You have glycogen, why don't you just use it? You want to save it as long as you can to keep you alive as long as you can. You don't know when the next meal's coming. And so you do that by gluconeogenesis. Make carbs from things that aren't glycogen. Okay? So by saving glucose for the brain, by doing gluconeogenesis, you spare glycogen. Glycogen sparing effect. Don't spend your glycogen unless you have to, basically. That's cortisol. All right, so here's kind of a summary slide. The last zone was zona reticularis, but I'll save sex hormones for repro. I just want to kind of end with the adrenal gland physiology with this figure. It's a nice summary figure. Let's kind of look at what we got here. Short term, long term. Okay, so think structurally. Short term, is that the cortex or the medulla? Short term, medulla. Long term, cortex. Let's look at that first, since we just got through with it. Okay, what we learned today is that there's a hormone called CRH, uses the portal system, stimulate the corticotropes to release ACTH into the bloodstream, right? So they kind of like show you here. I mean, the two main zones that are affected are zona glomerulosa fasciculata, aldosterone, cortisol. So what they say here is they say mineral corticoids, but you just have to know aldosterone. Glucocorticoids, you just have to know cortisol. And they say all the effects that we've been talking about. Retention of sodium, right? Increased blood volume, blood pressure. Proteins and fats converted to glucose. What's that? That's the answer. What's the right here? What is gluconeogenesis, right? Proteins and fats converted to glucose. That increases the blood glucose. You're saving it for the brain. But it also suppresses the immune system. That is one bad effect of cortisol. Short term, you get the heart pumping, increase the blood pressure. You're going to convert glycogen to glucose. Okay, you're going to dilate bronchioles, and basically you're going to reduce blood flow to the GI tract and increase the metabolism. So these are all the effects of epi and norepi. So let me kind of write some of those down for short-term stress response. So, short-term stress responses from elevated epi, norepi from the adrenal medulla. Basically, get your blood pumping, increasing the heart rate. Okay, you're increasing the beats per minute. That'll increase the cardiac output. That'll increase the blood pressure. Okay? You want to breathe more, oxygenate the muscles you need. So you want to dilate bronchioles, open them up. Bronchioles, as we'll learn, are the tiniest airways. And by dilating them, you increase the resistance to airflow. Decrease the resistance to airflow. Bring more air, fresh air to the lungs, basically. What else is there? Increase glucose. That's basically it. So that's a short-term stress response list for you. Next slide is zona reticularis. I said we'll kind of skip that. Just know it's there. They secrete the sex hormones. They may contribute to the onset of puberty, as I said. And it's premature to kind of go through this now, but what I always like to do is like, you study a cascade and like, oh, do I know it? And I made some practice questions here for you to kind of practice. Just make a note to yourself. Maybe I should look at those after I study it, and you can kind of check with me Friday if you want me to give you the right answer. But what I really want to get to is ovaries, testes, before time runs out today. The ovaries and testes are primarily studied in repro, but we talk about them in endocrine since they secrete the sex hormones. Okay, we'll do ovaries first. Here's an ovary. Well, the ovary on this picture is on the top there. It's a simplified picture. They're inside the pelvis in the female. In the male, the gonads are, in the scrotal sac, outside the abdominal cavity. Here, they're in the female, they're in the lateral pelvis wall. There's the womb, the uterus, should fertilization and implantation occur. We'll learn that later. Here's the vagina and the vaginal orifice down there. But we're just concerned with the ovary now and how it secretes estrogen. So we don't need to be concerned with the other female repro parts for now. So here's a picture of an ovary that's been sectioned open. And you can see there's blood here, blood supply in the mesovarium. It's going to bring us our gonadotropins like FSH and LH. And they show you kind of like all the different structures that develop in a normal menstrual cycle, 28 days. So I don't want you to think that they're all there at once. You kind of cycle through it every month. And what I want to do is talk about some of the formation of, we call it egg, right? Everyone knows an egg. It's the one cell that's fertilized by the sperm. And they form in the ovary. But I want to talk about the structures that support the egg, because those are the structures that actually secrete the estrogens, right? And so they're kind of shown out here. So the story begins actually during pregnancy in utero. Before a female is even born. What will become what we call the egg that is fertilized by the sperm. The name of the cell line is oogonium. And in pregnancy, the oogonium, they divide by mitosis. Okay, you got one oogonium, it divides and becomes two. And it divides and becomes four. The daughter cells divide, and they keep dividing. And this is how a female builds up the germline cells, the eggs. Now, at around the 7th month of pregnancy, this stops. You get the formation of what's called the primordial follicle. Now, a follicle is basically, I think of a jelly donut. You expect jelly in the middle. That's what a follicle is. There's something in the middle of a structure. In this case, it's the egg, the oogonium, okay? And there's a wall of cells that form around it. A primordial follicle has the oogonium, it's one cell, surrounded by many cells. So I'll draw like many flat squamous cells. That's a primordial follicle. It's surrounded by what are squamous cells. On the illustration here, they're the smallest follicles at the edge. They're always at the edge when you look for them on an ovary sample. Okay, so this arrests mitosis because when you put a wall of cells around the egg, it can't divide anymore. So however many follicles form, that's how many eggs you have throughout the lifespan, and the female isn't even born yet. It's usually around, books say, 1 to 2 million. You have 1 to 2 million primordial follicles before birth. And books usually say, at birth, you'll probably still have about that many. I mean, it's a big range, right? Point is, there's a lot to begin with. So let's say 1 to 2 million primordial follicles at birth. Of course, we know that as soon as you're born, you're not sexually mature yet. You have to wait about 12 and a half years. That's the average age for puberty in females. I have a 12-and-a-half-year-old daughter, and we're still waiting for the first one, right? First menstrual cycle. Of course, that'll be my mom's purview. I think I'm off the hook. But anyways, let's get from birth to puberty. When you get to puberty, there's some attrition of the follicles. You're down to about 400,000 primordial follicles. So puberty is about 12.5 years later, we're down to about 400,000. But that's about the time, puberty is when you start looking at the gonadotropins, FSH, LH, they arrive at the ovary, and they can start to stimulate the growth of these follicles to more mature forms. And you'll cycle through every 28 days. From now until menopause, which is a depletion of these. Menopause is about 50 years of age, 50.5 years, I think, something like that. So from puberty to menopause, you get a monthly cycle. Each cycle, pretty much what's happening is the gonadotropins, FSH, LH, they you get a cohort of about 20 of your bank of 400,000 to develop. One will ovulate, but you get about 20 to kind of develop more. Call it a cohort. After primordial, you have what's called primary follicle. So you have your egg. They usually call it an oocyte at this point, not oogonium. Oocyte equals egg. It's surrounded by a layer of cuboidal cells. cuboidal follicle cells. Primary follicle. Now, it's still immature. It can't really do anything. And when I say it can't do anything, it can't secrete the hormones yet. You kind of have to wait for further development. When a primary follicle develops into a secondary follicle, they're much larger and they're too difficult to draw. They look like this on the picture. Here's like, kind of like primordial, primary. This is kind of, these two are getting into secondary. This is what I usually try to find for a secondary follicle, late secondary, where you have many layers of cells around one egg, one oocyte. You even see bits of fluid start to form. That's secondary. Okay. And then the most mature one is called a graphian or tertiary, where the egg is here on one side. You have a big moon-shaped, fluid-filled antral. So I'm writing secondary follicle, graphian follicle. You could call these the quote-unquote mature follicles. They have the structures that can secrete the estrogen. Mature follicles secrete estrogens. So I said you select a cohort of 20. About 20 will reach secondary development, but only one will achieve dominance and go all the way and be the big graphian. That's the one that will ovulate. Ovulation is when the egg breaks out, as shown here, in ovulation, about midway through the cycle, day 14, right? And then it goes in the uterine tube and it waits for, what fertilizes it? Sperm, waits for sperm. Okay, well, we'll get to that in regrowth. For development, we talk about fertilization. But for endocrine, we talk about the structures that make estrogen. And those are shown here. I'm going to zoom in on the graphian. I'm going to point out two structures. This is a real picture from our collection. We have the egg, oocyte, down there. But we're concerned with the endocrine structures. Here's granulosa cells and theca cells. Okay, so what happens is, well, first let's note that. Granulosa, theca. You see those on late secondary, sometimes graphian, the theca and the granulosa cells. The theca cells will secrete not an estrogen, an androgen. They secrete androstenedione, and this will be under the influence of FSH, the follicle stimulating hormone. Theca cells secrete androstenedione, and it's transferred to the granulosa cells. The granulosa cells have aromatase, which will convert it to estrogen. Which have aromatase and will convert it to estrone. We noted it earlier, right? I wrote it on the board. But this is occurring in the granulosa cells. So that's why I want you to note that this transference is happening. And that's how you get estrogen in the body. Those larger follicles would do it. Okay. We did ovaries, so let's do testes. And for testes, it's a little easier to understand. I don't want to talk about any kind of like progression from before birth. Let's just kind of look at, in a sexually mature male, if you section open the testes, you have this duct system. There are these tubes that are highly convoluted called the seminiferous tubule. When you cut it open and make a microscope slide, you're seeing a bunch of cut tubes, some of which are blood vessels, so the testosterone can get in there. The seminiferous tubules have the immature sperm cells, basically. Okay, and we'll look at the details of that in the repro chapter. But the cells outside the seminiferous tubules in the interstitium are simply called interstitial cells. They secrete the testosterone. And I chose a picture where the interstitial cells are right next to a blood vessel, because you got to know that's how testosterone goes everywhere. It gives what helps the sperm develop right there, right? And it also helps develop secondary sex characteristics for males. Deeper voice, increased muscle deposition in the upper body. And there's no gender difference between boys and girls before puberty, like 3rd or 4th grade. But if you watch kids at the playground, boys tend to be better athletes, but that's totally socio-cultural. There's no physiological reason why they should be. I have this vivid memory of 6th grade, we had these relay races, and Albert Oliva, this girl beat him, Andrea Burries, and he was crying. It was okay, they didn't go through puberty yet. But we don't know this stuff. Before puberty, there's no physiological differences between boys and girls. If there are, it's socio-cultural. But when you get the sex hormones, then there are legit physiological reasons. So what you need to know about the testes is 2 things: seminiferous tubule, they have the developing sperm. We'll talk about that in another chapter. But the cells outside of them are the interstitial cells. Some books still call them the interstitial cells of Leydig. They secrete the testosterone. We've got about a half an hour left. In that time, I want to show you the slides you have to know for Friday's quiz. So we'll pick it up with thyroid on Friday. I still have to teach the thyroid histology. I'll do it now. But just know we'll pick it up here for lecture on Friday. I got to pull the slides out. It'll take me just a couple of minutes if you want to get up, stretch out your feet, go outside for a minute, for just a quick minute. I'm going to start as soon as I get the slides from there to there. Yeah, that's fine.